Hi, this is Soham. I'm going to talk a little bit about some of the code that I implemented for this project. I was primarily responsible for the RNN in task 2, but I also implemented some other files related to data processing and cleaning. I'm going to go over them kind of quickly because I don't have that much time in the amount of time allotted to me. In this class, this file data.py, we implement a lot of methods responsible for data cleaning and preprocessing. So there's a data loader class, which is then subclassed by these two classes. So we have an NSL data loader, which is specific for the NSL KDD dataset. What happens in this is essentially we load in both the training and testing set. We first kind of take the labels and turn them into their parent category. So for example, Smurf would turn into DOS in the after that. We then perform a label encoding of all of the class labels. So each of these DOS, probe, U2R, etc., get assigned a number, and that way the machine learning model can use it, because otherwise the categorical data is not quite usable. And then we perform a one-hot encoding of all of the other categorical features that are in the NSL KDD dataset. Later, when we start to train this model, we further kind of reduce the labels into just 0 for benign data and 1 for malicious data. The reason we do it in this two-step approach is just so that at a later time, we can sort of reverse engineer and retrieve the original class that a row is assigned to. That way we can do more comprehensive analysis of where our models are making errors. And in a report, you'll actually see certain graphs that show that some models end up learning to predict that all the data is benign because the benign data ends up making such a huge amount of the data. And the only way that we were able to do that is kind of through that two-step approach, reverse engineering or reversing to get the error frequencies. One thing to note about this class is for the one-hot encoding, we have to do it on both the train and testing set at the same time because there are some values in the training set for the categorical data that do not appear at all in the testing set. And if you are familiar with one-hot encoding, you will know that will cause kind of a shape mismatch. We also remove one of the one-hot encoded columns in order to reduce redundancy, which is, again, a process you may be familiar with if you are know about one-hot encoding. For the CIC data loader, we kind of do something similar. There's some processing that needs to be done with the file because there are some garbage in the column names, and some of the categories have unencodable data. And there's even a duplicated column. So we kind of clean up all of that. There's no categorical data besides the labels. So the only kind of encoding we do is a label encoding. And for the CSE IDS dataset, we used mostly the Friday port scans dataset in the afternoon. But our code is actually written in such a way that it could be used for any of the particular classes. And the LSTM class implements mostly the task 2 related code. So this is a class basic LSTM processor. What it does is it subclasses that data loader from before for the NSL KDD dataset, and it allows me to implement certain functions that are specific to the LSTM while allowing the class to be generic for the other tasks. So the only thing that the LSTM does differently is that it does a min-max scaling of the data. It specifically avoids the categorical data that was one-hot encoded previously. And we're very careful to make sure to fit the min-max scaler only on the training set and not at all on the testing set to avoid that kind of bias that could happen if we fitted it on a combination. We also, for the CSE dataset, similar thing. We also delete these two columns because they are filled with invalid values and there are more details in the report. And we replace all these invalid values, and there's more details in the report about our decision-making process behind that. We also implemented a version where we do not drop anything. Again, more details in our report about that process. One thing about the LSTM that's important is that the data is sort of time-stepped because it uses the previous few data to predict the current sample. And I have a lot of methods in here for plotting curves and a test method that is agnostic towards kind of what model is used and what training data is used. So it can be kind of adapted for the other tasks. And down here, you can see you can sort of specify different parameters for the model, and then you can just run them all at once. And when you run that code, what ends up happening is, so for example, you can see, I'll go in here, it produces some plots. So it produces some plots, such as a receiving operator characteristics curve, an error frequency curve. So this kind of shows what samples it incorrectly predicted. and learning curves for the data, depending on how many epochs are there. It also performs this text file, which gives you some information. It kind of appends. So it gives you information about the training as the epochs go by, as well as other information in text form so we can write specific things. It also saves the model. Another thing that's implemented is we have a random forest classifier for feature selection. So one of the papers that we read discussed talking about and like using a random forest classifier to sort of select some optimal relevant features. So whenever you use that mechanism, it provides a graph of kind of the relevancy score for each of the features that were selected. And that's sort of the principal result. So for the LSTM, what we ended up basically implementing to answer all the questions was we designed a simple LSTM classifier, the details about the structure in a report. And what that ended up accomplishing was we could train on the CSE IDS dataset, we could train on the NSLKD dataset, and more information about our experimental process, like the parameters that we used, are in our report. I don't have enough time to talk about sort of the test processes as well as all of the details.
Hello, my name is Han Kui, and I worked on the FNM portion of Task 2. Soham already explained how the data cleaning process works and how his code generates learning curve graphs and other types of data. So because we're doing a horizontal comparison with a simple FNN, I simply emulate his methods, but with an FNN model. Because of this, the FNN model is very similar to the LSTM model in terms of implementation. So I'm going to focus on answering Task 2 questions. And then I'm going to share my screen for the data examples. So the first couple of questions were if the RNN is a better model for detecting time series data. So with this NSLKD data set that we have, as one example, the accuracy is very similar. Here we have a slightly above 0.992, and here is slightly or around 0.985. So the accuracy differential is not that significant. Furthermore, we also tried doing this with the CIC IDS dataset with the similar results. Both accuracies are very comparable with approximately 0.998 and 0.995. So an RNN does not have greater accuracy to an FNN in time series data. We also experimented with the number of epochs for the LSTM because one of the other questions was if an RNN can handle long-term dependencies, and one of the types that can handle long-term dependencies is an LSTM. So with our data, we have the accuracies for 3, 4, and 5 epochs. And as you can see with these results, as in slightly below 0.990, above 0.9950, and then slightly above 0.995, the accuracy does increase over time, but with like diminishing returns. And that answers pretty much all the task 2 questions and the comparison of the FNN and RNN models.
How you doing? My name is Daniel Romo. I worked on task 1. Han Kui and Soham kind of already explained our data preprocessing and also our FNN model. The only thing I did different is I did use the recommended amount of nodes and layers that was set for task 1. The reason I did this is it just seemed that the accuracy rate started to decrease as I started tinkering around with the layers and the nodes. So basically, let me share my screen. When we take the subset A and test it against the unknown attacks, we get a 75% accuracy rate. So we all know what the subsets are. One of the things is the false positives for R2L were extremely high when they were when it was supposed to recognize that it was an R2L, it didn't. So that shows that it leans more towards the normal data than an attack. As far as the differences between A3, A4, and A1 and A2, so A3 and A4 are more towards unauthorized access, and since they don't have frequent sequential patterns in their data, like DOS does, they're not really similar in that aspect. And so there definitely are differences. A1 and A3 are, in my opinion, not in the same attack category. If we take the model and create two more subsets, we have subset B and subset C tested against the unknown attacks. Subset B was a 75% accuracy rate. Subset C was a 79%. So it did get a little bit better. I think C was a little bit better just because it had one of the attacks for the unauthorized access, so it was able to predict better, in my opinion. And then also, I would say that as far as accuracy goes, predicting unknown attacks, it's not ideal. There are other options that I would assume that would be better, just because it did miss quite a few attacks. So as far as going through subsets where the attacks are unknown, and I would say that it's not ideal for this.